right, so today we are going to look into what we call the machine learning based modeling based on the principle of let the data speak, a generic or general framework or generic framework. So under the important clarification series. So what exactly we want to do is we want to provide guidelines with some of the knowledge we've acquired. It is time for us to move, practicalize what we've learned, lay your hand on very interesting area that you want to work with, and then start building your machine learning based model, and then see how you can then make it better. The generic framework, we've been seeing this before. However, I want to put a touch on it. So this is a kind of a generalized framework, but today we are going to put some special clarification and guidelines on how we can go about each of them. Now, as we know, data is very important. So data is very important, and especially when we base on the principle of let the data speak. Let the data speak. So principle, let the data speak. Let the data speak principle means we avoid too much assumptions. For example, saying, oh, the algorithm that is better is this, I'm going to use it. No one can tell you the algorithm that is better for your own data set. Let the data speak. That data will indicate. The data we find that when you put the data into the algorithm, build the model, the performance will indicate if this algorithm is better for this data. Because no matter how similar data, two data sets might be, they might actually not be understandable to a particular algorithm. And there's no algorithm that is always better than the other. So we have to really see in real life how it can perform. However, in order for you to be able to be fair to all the algorithm you are using, you have to let the data speak principle guide your procedures. Because let's say now we're starting with data preparation, feature engineering, then we have discussed all this. You can check them out in our previous videos. Then under the data modeling, we all know that data modeling is divided into training and testing. See, to appreciate this, let me show you this. What is happening inside this data modeling? What is happening is this. This is what is happening. So let's say you're going to have training examples. So let's say we are dealing with these images. These are training images. You want to be able to train a model that can identify or differentiate between each of these images: tomatoes, apple, and pears, and some animals. So the first thing is to extract the features. You extract the features, extract the feature out from the image. The feature extraction principle, you can do it manually, you can use some software to do it. So, and then once we extract this feature, then you can provide the features now into the training, you put the algorithm is going to act here. The training process is you give the feature to the algorithm, and then you tell the algorithm that this feature that is coming in belongs to Apple. The next feature belongs to this. The next feature coming in belongs to, so it will be training it, so that is training level. As the feature combination are coming in, maybe we have like a X1, X2, X3, up to as many as possible features. So as it is coming in, you are telling the system that, okay, this is the label for it. So once you are done, the system carry out what we call training, and we already discussed how do we partition for training. Divide into training set and testing set, or you use cross-validation. Sometimes you can divide into three: training, testing, and validation. We discussed this earlier. Now, so now you have this is the learn model now. This is the final model that you have generated. So after that, you move to the testing stage. This is the testing. Now you have a particular image, test image that has never been seen before. So this one you are going to use must not be part of those that you have used in this particular place. This is a totally new one. So that was why when you are doing your building of model, you divide your data into, the very common one is divided into training and testing. Sometimes if the data is much, you have so much data, you can divide into training, testing, and validation. Both testing and validation set will be used for checking the system performance, but in most cases, people just go for training and testing. So the condition for testing set is anything you want, any images or any sample you want to use, this sample you want to use for testing must not be present in the training set. Otherwise, the purpose of training is defeated. So we are bringing a totally never seen before output by the model, and then we are going to now ask the model, we extract the feature, and then we provide the feature to the learn model. The model we build here, we bring it here. So it will receive this image. You can see now that the AI we used to give the label, although we know the label for this, but we will never provide it for the learn model. We let it predict for us what is this object that is coming in. So if once it produces its own prediction, then we now compare the prediction to the label that we have. We have the label, but we keep it away from the learn model during the testing set. But during training set, we have to keep showing it the features and at the same time the label so that it can train to recognize it. So once it is fully trained, then we use it to check. This is testing to see if it's able to predict correctly. Let's say after we brought in like maybe 10 new samples now for testing. Out of these 10 samples, it's able to correctly predict 9 out of 10. That would be 9 over 10 times 100. That's a good percentage accuracy. That is, it correctly predicted or identified 9 out of 10. That is excellent. Of course, we always want to get 100%. So what I just described now is what is taking place in this section here. This is what is taking place here. When you say data modeling, that is what is taking place. I just expanded it. There you are going to have training and testing. And now you are going to check the performance. If it is classification problem, then you're going to have accuracy. You're going to have confusion matrix. But if it is regression problem, then you'll be talking of root mean square error and the R square correlation coefficient, and also further performance measure you can use. Now, this is time for you to check the performance measure. In the example we did now, we say 9 out of 10. So 9 out of 10, that is, if you take it to percentage, that's going to be like 90%. Yeah, it's good. But for medical, we want more. It's not enough. We want to be able to get even more. In that case, okay, we want to push it more. You might have to go back here. This is why it's an iterative process. So going back here means you might have to do parameter optimization here. Hyperparameter. These are the parameters that affect the model itself. You do hyperparameter optimization here. You keep doing that until the result is fully okay. Until the result is fully okay, satisfy you. Sometimes you might not be able to get it fully okay. Then it's time for you to change the algorithm. I was using KNN before. I changed to SVM. Use simple algorithm first, KNN, decision tree, naive Bayes, then you can start go and neural network, SVM, and the likes. So when you go back here, you can do two things. You can do hyperparameter optimization, and you can also change the choice of your algorithms. Sometimes individual algorithms might not work. We might have to do what we call ensemble, where we put together different algorithms to collaboratively solve the problem. These days, it has always been one of they are always the winning models that always won the competitions, ensemble. Now, once this is done, sometimes just going back to data modeling might solve your problem, but sometimes it might not. You might have to go back here. See, you might have to go back to feature engineering. Maybe your feature engineering, the feature are not properly formulated. You might have to do some manipulations. So, or sometimes you have to go back to data preparation. Maybe you had the wrong data set collected. So in that case, you have to go back to the beginning. There is an iterative process that is always going on now. So this is what happened at this point in time. So having clarified this, regarding hyperparameter tuning, we can also look at it from this point of view. So you start here, you have the data gathering is going on, you do your data preprocessing, we call it data preparation stage. However, the question is, what amount of preprocessing is enough? We had a video already earlier on this, a section where we discussed how much of preprocessing is enough. Don't waste your time too much on preprocessing. So let the data speak. We'll come back to that to guide us. So model building means you're going to build the model here, then you are going to do the testing, then you check. See, do we need to refine the model? That is the performance not okay? Yes, the performance is not yet okay. Then do hyperparameter tuning. You have to go back. So you keep doing this looping until you are satisfied. You build the final model. You have model validation, prediction using the model to check your result, and then analyze your result, identification of hotspots, what are the pending tasks, what are the, as you are doing the research, idea will keep coming along the way. You have to keep documenting them. Some of them will become what we call fence in, and some will become fence out. Fence in, this idea that you never started with as you are carrying out your research work, your project is going, ideas came, oh, I can do this, you put it there. Oh, I could do this, you added it again. These are called fence in. But there are fence out. As you are detecting them, you realize, oh, if I had this is very interesting, I think I can investigate it together with my work. Or you find out that it might be too much for you. Because, research project is time bound. You want to finish at a particular time. So in that case, you might not be able to put everything or inculcate everything into your project that is ongoing. In that case, you put them as fence out. Fence out means this, we can look at it in future. So they will form part of your future work recommendation. Future work recommendation when you are documenting your machine learning report or outcomes. This is very, very important. Now, so what we want to clarify, based on this understanding of the procedure we just explained to us, how it is always in a loop. There's this particular point that need to be clarified, which I call the MS-based principle of modeling. MS-based machine learning-based modeling based on the principle of let the data speak. Now, so the first thing is you have to carry out first experiment. I call it experiment number 1. What is experiment number 1? Here you're going to use the original data set as much as possible. Use original data set as much as possible. Avoid too much preprocessing at this stage. I have to clarify this. Avoid too much preprocessing. See, because sometimes some preprocessing are not necessary, like normalization. So if you normalization might bring down your result. Sometimes normalization brings down your result. So, but sometimes normalization can improve your result. So when do I know, how do I know that normalization will increase or improve my result? This is why I always tell people, first of all, carry out the first experiment using the original data set and document your result. Because there's going to be comparison. There's going to be comparison. So for this one, avoid, except if there is any preprocessing that must be done compulsorily. For example, there are missing value. Even some platform will still allow you to use missing values, do modeling use even while the missing values are there. So, however, sometimes you need to fix the missing values, which is okay. We already discussed previously how to deal with the missing value. You can check out some of our previous videos, missing value treatment and outlier treatment. But the point here is make sure that you carry out this experiment as much as possible using the original data set. The least possible, do only the compulsory preprocessing. Preprocessing that if you don't do it, it will not go ahead, it will not work. Your model will not run. Then, in that case, you have to do it. but don't do any other cosmetic, what I call cosmetic preprocessing. Yeah, there are so many preprocessing you can do. In fact, in data science, it is established that 60% of the time for model building is spent on preprocessing. See, 60%, more than 60%, by the way, of the entire data science project development life cycle is spent on data gathering and preprocessing. Now, that is why the principle of let the data speak is being proposed to actually make life easy for people and hopefully get things in a better way. So once you use the original data set, then try to make use of hyperparameter tuning, the optimization. You have to check it also using the original data set. Also try different machine learning algorithms. It's very important. Start from the simple. See, start from simple to the complex. Don't start machine learning algorithm from complex ones. You might miss the important algorithm that might solve your problem. Because sometimes a particular data set might need a very simple algorithm to solve the problem, like KNN, K-nearest neighbor. We call it lazy classifier, but it could be very powerful. We have seen someone who used deep learning to solve a problem and was able to get only 75% accuracy. However, with a simple KNN, we were able to get 95, even though we were not yet done with hyperparameter tuning. Just imagine how many percentage increment. See, because he went for bigger, complex because of the name. No, it's not a matter of name. Let the data speak. Always remember that. First of all, go for very simple algorithm. Use original data set as much as possible. Now, and then move on. Once you have done that, you have run experiment on the original data set. Then you can then move for that. Maybe your result is bad, no worry. You can always go back to do as many pre-processing as possible. So now, another thing to check for is if it is classification problem, check for class imbalance in the data set. If you are solving classification problem, check for what we call data class imbalance. Because if there is class imbalance, there are two things you have to do. And what is class imbalance? Class imbalance means you want to solve a classification problem. Classification problem means maybe you have two classes. You want to predict if there's going to be rain or not, no rain. There'll be rain tomorrow or there's no rain. This is two-class problem. Yes or no, class 1 or class 2. However, in your data set, the data set provided for you, you had like samples of when it rained were like maybe only 20. There were 20 days that it rained in the data set you had. And they're like maybe 1,300 from the no rain class. This is rain. There's rain here, only 20 samples. For this one, 1,300. This is called class imbalance. Class imbalance is going to affect the result of your modeling. You see, you only have 20 from this class, you have 1,300 from this class. It means the model will be exposed to 1,300 of the no rain, so it's likely going to predict everybody as no rain. Because it might not be able, this is too small compared to this. So this is called class imbalance. Sometimes, another example, you want to predict if somebody is sick of diabetes or not. So, but then they give you data set from the clinic. There are like 50 patients with the disease. They are positive patient, that's 50. And there are like maybe 900 negative people that are not sick. You know, this is normal in a community. Number of LD people should be more than number of sick people. This is a natural thing. So imbalanced data set is a natural phenomenon. Rain cannot be rainy every day. Depending on where you come from, in some country, rainy is the exception. So maybe in a whole year, maybe they get like 20 rains or 10 or less. Why in some other countries, so many days? However, for disease modeling, in a normal community, the number of sick people should be less than the number of LD people. In other words, more people should be more healthy compared to those that are sick. So when you have 900 negative class samples from the negative class and 50 from positive class, it means this model will be exposed to more negative, which means even sick people might be predicted to be not sick later on. So this is called imbalanced data set. When the number of samples for each class, they are not the same or they are not close together. You might not have the same value. It's okay. One is like 50, one is like 500, the other one is like 650. This is okay. This is no problem. See, 500, 650, that's still fine. You see, once we have enough for training for both, it's fine. One is 500, the other one is 550. But when the number is becoming really huge, different, 20 to 1,300, 50 to 900. In fact, there was a problem where we had 10 samples from one class against 990 from another class. This is really, really big imbalanced data set. But yet, this is the natural data set we get. We have to model it. So if you check and there's imbalance, then you have two options. You have to do experiment you have to do two experiments. The first one is called oversampling. And the second one is called undersampling. Sorry, undersampling. This is undersampling. Undersampling. First one is oversampling. Oversampling means you increase randomly these 20 samples to become 1,300 also. So that each of them will have 1,003, 1,003. They become balanced. That is oversampling. There are different sampling techniques that can be used in this particular respect. So once you do that, then you run your experiment using balanced data set and see what you get. Okay, now, so the third experiment is undersampling. Undersampling means, let's say in case whereby this number of samples is a little bit reasonably okay. I have like 100 in one class and 600 in another, 650 in another class. I can bring this 650 down, bring it down to like 100, 100. So I remove randomly from this. So I have 100, 100. So I carry out experiment using 100 sample from class A, 100 sample from class B. This is balancing using undersampling. It means you undersample the majority class, bring it down. So once you are done with that, of course, when you have system like this, it's very challenging. So it means you have to reduce this to only 20. That is going to be very small. But then you can use, since the data is very small, you can use cross validation to solve that problem. So you can even use leave one out cross validation, in which you divide it into the number of samples and then you train as many as possible using one to test for each case and you find the average, because cross validation is often used when the data sample they are very small. Now, so that is oversampling and undersampling. Now, you've gotten 3 experiments now. Compare their results. You see where your result is getting better. Are you getting good results in the original data set, or in the one oversampled, or in the one that is undersampled? You have to look at that, comparing. There's always need for comparison when you build model using machine learning principle. Now, once you have the results, then compare the results, and discuss the result. Compare and discuss the result. Discuss them. What do you see? What do you notice? In real life, we have noticed sometimes oversampling will bring you better result. Sometimes undersampling will bring you better result. And sometimes the original data set will bring you better result. Even when there's oversampling or undersampling. We've seen the problem whereby we notice class imbalance, but yet the original data that we didn't balance gave us the best result. This is in line with the principle of let the data speak. I have seen students, the moment they found out that the data is imbalanced, they went into experiment straight using balancing method, oversampling, undersampling. When they submitted their report, I said, okay, where's the result of original data? They said, we didn't do it because we noticed that the data is imbalanced. I said, no, it's not correct. You might have missed very important insight from this data. So go back again, run the experiment number 1 using the original data. Let the result be bad. It's okay. We want to see what the data is saying. That's the principle of let the data speak. Let us know what the original data came with. What are the characteristics that it came with? Don't ignore it. This is a very common mistake that people often make, actually. They ignore the first data set because they think, oh, there are so many imbalanced data sets. No. Run the experiment with imbalanced data. Let us see your results. Then do the oversampling, undersampling, then compare the result. Then you are moving. Then you see which one is working for you in a better way. Now, a clarification I would like to make before we continue on this is this oversampling and undersampling. We have to take note, especially oversampling. In the undersampling, we are not playing with the data. You just remove excess from this, become 100, 100. But oversampling, we are repeating data set. This is why I have to make a point. For the oversampling, take note that your testing set must be normal. Don't oversample your testing set. It means once you take the data, break the data into two. Training set, testing set. The testing set will be imbalanced, the training set will be imbalanced. See, we call something stratification. When you are breaking down your data into training and testing, when you use stratify approach will make sure that the data is broken down in such a way that both training and testing will have a representative value from both classes. This is very important. We don't want a training set whereby all the 20 samples from this are in training, is 0 in the testing. For 1,300, maybe 700 is here and also the remaining here. But for this one, it has no representative in the testing case. No, we don't want it. But when you use stratified sampling approach, it makes sure that even though the number of samples from one class is low, it will share them between training and testing appropriately. Now, once you have broken down your data into two, training and testing, keep away the testing set. Don't normalize it. Don't oversample it. What you need to oversample is the training set. Because what you are trying to do is you want the model to see as many samples from each of the classes. So we increase this 20 randomly. You keep increasing it randomly up to then you go to get, maybe after breaking the data into two, now we have like maybe 15 samples here in the training for this one, while we have 5 for testing here. And this one is having like maybe 900, and then the remaining maybe 400 is there for testing. That's okay. So this 405 for testing, we will not do any oversampling for them. Keep it. But you can then oversample this. Keep repeating 15 until it becomes 900. Then you can train. Once you train, you bring in the testing set, which is not oversampled, original one. Why? Because in real life that you are going to be using the model you are building, the data is naturally imbalanced. When you go back to the clinic and collect data, you're going to see a lot of people that are healthy and lesser people that are having the disease. This is a natural population. So your testing set must be imbalanced. Leave it as original as possible. So let us pay attention to that. It's another mistake that people do make. They oversample the data generally and then divide it into two. It is wrong. You don't oversample your testing set. Let it remain normal. You'll be more of one class than the other. It's okay. But the training set is the one that you need to oversample so that the training procedure will be able to expose each of the classes to as many numbers as possible. Towards the end, then continue with, here we have, if there's imbalance, then we enter this loop, do 2 experiments. If there's no imbalance problem, then you don't need to do that. So and then you go into continue with normal or original data set as usual. And you only have imbalanced data set if it is classification problem. Also take note of that. If it is classification problem, you may have imbalanced data set, not always. So you have a data set that is 600 against 650. To me, that is not imbalanced. Just ignore, continue with your work. 50 is not a problem. It is when the number is really wide, then you start getting, and by the time you run the experiment, you are likely going to see the effect of it. And then you move on to experiment number 4. Either you are doing regression or no regression. So in regression, you will not have this because there's nothing like oversampling or undersampling in regression. We don't have data imbalance in regression. Now you do feature selection to get better result or make the model light. So of course, this could be optional. So if you have gotten very excellent result either here in the original data or when you're using your oversampling or undersampling, that's okay for you. You already achieved 99% accuracy. What am I looking for? It's okay for me. However, you may need to do feature selection. Feature selection is a way to reduce the number of features. Sometimes it makes you to get better result. You can check out our video on what I call cost of dimensionality. Cost of dimensionality. The more the number of features, the more the number of samples you need to get good result. And sometimes the number of samples are even limited. So which means if the features are many, you got to, it's the data from your client, 70 feature with only 300 samples. Ideally, with 17 feature, we should be getting like 10 raised to power 17 samples, which is not possible now. So you have to do feature selection to get better result in most cases. So, however, even when you have gotten better results using original data set, then another advantage of feature selection is you can build what we call a light model. See, you want to make the model light. That is very not heavy computationally. Because if you are selecting like 17 features, that's going to be a long computational complexity on the system. Imagine if you are getting 99% with 17 features, and I'm able to bring that feature back down to 5 from 17. If we both build a model for a medical center, which one do you think people will use? They will use my own because I'm having only 5 features, while you're having 17 features, and we're getting the same result. So sometimes feature selection make it easier for the client or for the patronage to be very good. So when people say that, oh, we have a system that can predict a medical history using just only 5 features, you need to do only 5 medical tests. And another one say you need to do 17 medical tests. That is too much. Even if I can bring that 5 to 3, I would try it. The lesser the number of features that can achieve the same result, then the better for that kind of modeling. So in that case, you have to do the feature selection, which I say is always optional. It's up to you. So if you think you have gotten the best thing, we don't care about computational, whatever, you are good to go. But then for those who want to look at the advantage of feature selection, either to get better results or to make it light, building a model that is easier to get the number of features, it's cheaper to get the number of features, it takes lesser time to get the number of features, then you might have to go in this process. And last but not the least, you repeat the entire process in a loop if necessary. If after trying all this, you didn't get what you are looking for, you might have to go back all along again and start maybe pre-processing was not properly done. That was why we show us this initially, that look, you can always go back. See, you can always go back and then change the algorithm once again, do the feature selection again. So it's a system that is kind of iterative for you to get better result, or as the case may be. So in the experimental setup, finally, so you can see what I'm discussing here. It becomes so many. So to make it easy for the people that will read your work, because even if you are not a researcher, if you are working on, if you are working on machine learning modeling, you have to write report, because your report is the outcome of your modeling. You see, it's not building an equation. No, you have to tell us what is the value of hyperparameter you use, because when I pick your report, I must be able to repeat your experiment. If I cannot repeat your experiment, then it becomes useless. And that is why it's good after you have finalized your work, it's good to have a very clean experimental setup. All the procedures you have taken, document them in a very nice framework. Okay, I got the data, I combine them together, I do pre-processing. What are the pre-processing I did? Tell them everything you have done. We divide the data into 70-30. We have seen paper that got published. Of course, these are junk journals. They didn't tell us what is the percentage of breaking down the data. That means you cannot repeat the experiment. But if you don't know the percentage of data partitioning, there's no way you can repeat it. It's a very simple information and very, very vital. for the validity of the research. So once you see a paper that does not have the percentage split, just ignore it. It's not a paper to reckon with because it is not valid. Because if you cannot repeat an experiment, then there's no way how the paper got accepted is even questionable. So these are minimum information that has to be provided. Then you have to tell us whatever you have done. You can see experiment 1, this is undersampling using SMOTE. SMOTE will do oversampling for you. It's one of the methods for oversampling in imbalancing. We call it SMOTE. There are so many other methods anyway. So you do with SMOTE, without SMOTE, you compare them. You did a grid search, you didn't do a grid search, I use simple hyperparameter optimization. Then I build an ensemble. If you decide to build an ensemble, tell us every step you have taken that finally culminated in your work. In that case, people can pick up your report, either in your online GitHub or anywhere you put it, or a published work, and they can repeat your experiment, and they can then extend what you have achieved. So this is procedure that must be followed when you build machine learning based model in what I call following the principle of let the data speak. So don't spend too much time on preprocessing thinking your data cannot be good. No, go ahead and use your experiment and come back to preprocessing if there's need for more preprocessing, like normalization and also for that preprocessing. Sometimes you don't need them. So they're just optional. So this is what I believe we can have for the day. I'll be sharing with us the kind of a generic document that I built that you can always use it when you carry out your experiment to do your reporting of what you have done. So I'm going to share it on the platform. I call it how to write report of machine learning based experiment when you do data modeling. So we have all these procedures will be explained, how you write your abstract, how to write introduction, then going to experimental details, what you have to provide, doing feature selection and conclusion writing, and also for others. So all this also, we already had a video in the beginning that explained how to write abstract, how to write introduction, and also further when you are modeling using machine learning and the related concepts. So this is what we're going to have for the day. Thank you very much for listening, and I wish you all the best.